Welcome to clickmeproject.com. Here we are discussing about area delay power efficient fixed point LMS adaptive filter with low adaptation delay. In this project mainly focused on the adaptive filter in partial power delay multiplier in various multipliers. These mean square Addons are a class of adaptive filter used to decide a filter by binding the filter coefficient with related to producing the least mean square of the error signals. In our error signal based on the difference between the desired and the actual signal. In our previous paper, the proposed fixed point adaptive filter with a low adaptive delay for optimizing balanced pipeline across the time consuming combination blocks of the structure. The adaptation delay of our M cycles amount of delay introduced by the whole of adaptive filter structure consisting of the initiate impulse response filtering and the finite impulse responsing and the weight response update process. The proposed design is bounded is by be more efficient in terms of the power delay product and the energy delay product compared to the existing system. In our enhancement, we proposed a efficient multiplication stage in FIR filter technique. In this, we use the partial product delay multiplier method for FIR filter, which gives a delay effect for the bit series of input based and partial multiplication that gives additional result of each delay blocks. This method gives least MSC values and the less energy delay products. The CTS architecture can implement in the VLSA platform in the form of visual language. We use the Addons to provide visual language for our architecture. Important characteristics of array multiplier allow pipeline. Execution of separate multiplication overlap. The long delay of carry propagation addition must be minimized. Achieved by replacing a CBA with several additional rows allows carry propagation for only one position between consecutive rows. To support pipeline, all cells must include latches. Each row handles a separate multiplier and pair. Register need to propagate multiplier bits to the destination and propagate completed product bits. It's mainly focused on Java project very efficient and very reduced in our project. The two basic operation generation and transformation of partial product can be managed avoiding the overhead and speeding up multiplication. Iterative array multipliers consist of additional cells, each forming a new partial product and adding it to previously accumulated partial product. Gain in speed obtained at the expense of extra hardware can be implemented so as to support a high rate of pipelining. The existing work on the DLMS adaptive filter does not discuss the fixed point implementation uses, location of radix point, choice of word length, and coordination and work sets of computation, although they directly affect the conversation performance, particularly due to the recursive behavior of the LMS algorithm. Therefore, fixed point implementation issues are given adaptive impulses in the pattern. Besides that, we present here the automation of our previously reported design to reduce the number of pipeline delays along with the areas sampling period and the energy The proposed design is bound to be a more efficient in terms of the power delay product and energy delay product compared to the existing structure. We review the LMS algorithm and in section 3 we discuss the proposed architecture for this implementation. In this block diagram, referring the flow of our process. First of all, we give the input to the input signal. That input signal are arranged into the bitwise. The bitwise arranged input signals passed into the pipeline structure. The pipeline structure based on the 4 steps. We know that the fetch and instructions and execute. Okay, and then finally we pass our output into the shift register. The shift register generate output at each clock signal generation based on. Then finally we give the shift register output into the adder circuit. The adder circuit finally generate our single output signal. These are our working flow of our process. In this block diagram mainly focus on the efficient design of our process. In this structure reduce our radio and the delay and also reduce the power consumption also. This is our working structures. Now we are going to discuss about running procedure of our project. In our project we have 4 steps. First step we check the syntax error, then second step we generate the Addons schematic diagram, then third step we generate the technology schematic diagram, then finally we generate the simulation waveform. Now we are going to the first step. First select implementation, then select tap module, then select check syntax. In this step, check the syntax error of our program. In case of any error and warning that displayed in our console block. In our program we have no error, therefore we are going to the second step. Please select view RTL schematic and run that. Now we are going to generate the RTL schematic diagram. After the completion of our running process, add, then create schematic. This is our overall RTL schematic diagram. FIR in, clock reset, these three signals are our input signal. FIR out, these signals are our output signals. This is our internal block diagram of our RTL schematic diagram. Now we are going to the third step. Please select Wave Technology Schematic and run that. Add, create schematic. This is our overall technology schematic diagram. Then select. This is our internal block diagram of our technology schematic. In this technology schematic diagram consists of number of LUTs and flip-flops. Now we are going to the final step. Select simulation, select main function, then select simulate behavior model and run that. First set the initial condition, set the clock value to 0, reset value set to 0, give the input signals, and run our program. Then again change the clock value set to 1 and run that. This is our reset condition value. Change the clock value to 0 and set the reset value to 1 and run our program. Then again change the clock values simultaneously, zeros and ones, and run. Now we generate the output signals. Every positive clock cycle we get a different kind of output. This is our overview of our simulation waveform. Now we complete our running procedure. Thank you.